Welcome to the Explainer. Today, we are diving into one of the most powerful ideas in all of machine learning, ensemble learning. And at its core, it's a really simple idea. A committee of decision makers is almost always way smarter than any single genius.
To really get our heads around this, let's start with something you've probably seen. Think about the game show Who Wants to Be a Millionaire? The contestant is stuck. They've got a few lifelines to choose from. Which one do you think works the best?
Yep, it's ask the audience. It's not even close. The collective wisdom of a random crowd consistently beats the single phone-a-friend expert. Now, this isn't just a fun piece of trivia. It actually points to a deep truth about how to make really accurate predictions.
This whole phenomenon, what people call the wisdom of crowds, it's not just a gimmick for a TV show. It's a fundamental principle that helps solve one of the biggest problems in machine learning.
Think about one of those classic guess how many jelly beans are in the jar contests. Any one person's guess could be completely off, right? But the average of everyone's guesses is almost always shockingly close to the actual number. And why is that? Well, it's because all the individual mistakes, people guessing way too high, people guessing way too low, they all tend to cancel each other out, leaving you much closer to the truth.
So, in the world of machine learning, this idea is actually formalized in something called the no free lunch theorem. And what it basically says is that there's no single magical algorithm that's the best at every single task. A model that's a genius at identifying cats in photos might be completely useless for predicting the stock market.
Okay, so if one genius model isn't the answer, what is? Well, you build a committee of models. And in machine learning, this incredibly powerful idea is called ensemble learning.
The process itself is actually pretty intuitive. First, you just train a bunch of different models. These can be totally different types of algorithms, or even the same algorithm just trained on slightly different data. Then, you let each of those models make its own prediction. You let it cast its vote. And finally, you just combine all those votes to come up with one final, much more reliable decision.
It's really just like trying to get an accurate temperature reading in a room. You know, one thermometer might be a little off, but if you take the average reading from 5 different thermometers, you're going to be much, much closer to the real temperature. So let's dive in. There are 2 main ways we can build these powerful committees of models. So let's start with the first strategy. It's called bagging. And don't let the kind of silly name fool you. This is a really clever technique for creating a diverse team of models, even if you only have one data set to start with.
Bagging is short for Bootstrap Aggregation. Now, the secret sauce here is a concept called resampling with replacement. Just imagine you have a big bag filled with all of your data points. You reach in, you pull one out, you write it down, and here's the key part. You put it back in the bag before you draw the next one.
You just keep doing that over and over to create a bunch of new training sets. Each one is a little bit different from the original and a little bit different from each other. Then you train a totally separate model on each one of these unique samples. So now each model has a slightly different perspective on the data. Finally, you just average out all their predictions.
So why do all this? What's the big payoff? Well, bagging is absolutely brilliant at solving a problem called high variance. So imagine a model that's like a really nervous driver. It overreacts to every tiny bump in the road, or in this case, small changes in the data. Bagging helps calm that model down. It averages out all those jerky movements and creates a much smoother, way more reliable prediction in the end. And that kind of stability is everything in fields like medical diagnosis, where you need to be confident in the answer.
Now with bagging, all the models are trained completely independently of each other at the same time. This brings us to the second big strategy, boosting, which is a whole different ballgame. It takes a sequential approach. It's less about creating a diverse, democratic committee and more about building one single super expert piece by piece.
So let's talk about boosting. The whole idea here is that each new model you add to the team is specifically trained to fix the mistakes that the previous model made. It's all about focused, step-by-step improvement. And boosting starts with this incredible premise. You can take a whole bunch of weak learners. These are models that are barely better than just randomly guessing. And by combining them in a really smart, sequential way, you can create one single, incredibly accurate, strong learner. Okay, let's just walk through how this works. Using a famous algorithm called AdaBoost. So picture our data set. To start, every single data point is treated as equally important. It has the same weight. We train our first simple weak learner on this data. And, it does an okay job, but it's definitely going to get some things wrong. Okay, now here comes the magic. The algorithm looks at every single mistake that first model made, and for every data point it got wrong, it basically says, okay, you're now extra important, and it cranks up that data point's weight. And for the ones that got right, it dials their weight down. It's like a personal trainer telling the algorithm, hey, you're weak on these exercises, so we're going to do a lot more of them. So the next weak learner is trained on this new reweighted data. Now, it's forced to pay way more attention to those tricky examples that the first model messed up. And this cycle just repeats over and over. Find the errors, increase their weight, train a new model. Each model becomes a specialist at fixing the mistakes of the one before it. This intense focus on the hard cases is why boosting is so amazing at things like credit card fraud detection, where finding those rare, difficult examples is literally everything.
So now that we've seen the what and the how of these ensemble methods, let's talk about the why. Why does this committee approach work so unbelievably well? Well, the answer comes from a branch of statistics called estimation theory, and it gives us the actual mathematical blueprint for building the perfect team.
According to this theory, a perfect expert, whether we're talking about a person or an AI, really needs two key qualities. First, they have to be unbiased. That means, on average, they get it right, and they don't have some kind of systematic error. And second, they need to have minimum variance. That just means they're consistently accurate. Their predictions aren't all over the place.
So, how do we get the absolute most out of our committee of models? Well, the math is crystal clear. It tells us there's an optimal way to combine all their votes. It's not as simple as one model, one vote. Instead, we need to give more voting power to the models that have proven they're the most reliable.
To put that more simply, we just don't treat all the votes equally. The models with a better track record, the ones with the lowest error rate, get a much bigger say in the final outcome. And by doing this, we can mathematically guarantee that we're getting the most accurate possible result from our committee.
All right, let's do a super quick recap of everything we've talked about. First, the no free lunch theorem reminds us that no single model is ever perfect. The key to better accuracy is combining diverse models into an ensemble. Bagging is one way to do that. It creates diversity by training models on resampled data, which is great for reducing variance. Boosting is the other way. It builds a super strong model by forcing new models to learn from the mistakes of the old ones. And finally, we know that the best committees are the ones that give more influence to their most reliable experts.
And all this leaves us with a final, really big thought. As AI continues to just rocket forward, what's the better path to the next great breakthrough? Is it trying to build a single, smarter, genius model? Or is it about perfecting the art of conducting an even more sophisticated, more powerful committee? The future of AI might just hang on that answer.